In that case, we'll kind of return to methods for approximating waves later on after we introduce the WKB method. And that'll also come up in sort of the last main module, which will be on homogenization. So today I want to introduce the WKB method, named after Wenzel, Kramers, and Brillion. And this is taught a lot in quantum mechanics classes because it's relevant to equations in quantum mechanics. And the idea is that it's a method to approximate solutions to differential equations, could be ordinary or partial, with spatially varying coefficients. And the idea is not terribly complicated. It's just making a specific assumption about the kind of asymptotic approximation you're going to make that's going to involve an exponential function. So this dates to the 1920s, and in particular, the study of the time independent Schrödinger equation. And this describes sort of the quantum mechanical counterpart to Newton's second law, right? So sort of like force equals mass times acceleration for quantum mechanics. And so it's a fairly harmless looking ordinary differential equation. The twist is that you have this slowly varying function of x, which serves as the coefficient of the 0th order term, okay? And you often think of this as resulting from some sort of energy potential. And this function physically is often described as some slowly varying potential energy. And the ansatz that we're going to make is that the solution is the product of slowly varying and exponentially varying terms. Okay. So before we get into this in general, we'll start with a motivating introductory example. We're going to apply the ansatz, and then we're going to break things out into hierarchies of different orders of epsilon, as we've done for method of multiple scales, regular perturbation methods. So a lot of this will feel similar to methods that we've applied before. It's just that knowing that I have some slowly varying coefficient like this is going to suggest a specific kind of ansatz that I would want to use. Similar to how, with all the methods we had for asymptotically approximating integrals, we're sort of triggered by the particular form of that integral. So our intro example here, okay, and we're sort of roughly following chapter 4 in Holmes for this module of the course. We're going to consider in particular epsilon squared y prime prime minus q of x, which is now not going to involve any epsilon y. This is equal to 0, okay? So not quite the form of this formula here, okay? But you can imagine that if we divide through by epsilon squared here, and then we're going to have all of our x and epsilon dependence as a coefficient of y here, okay? But things are a little bit easier to see here if we write it out like this, and then it becomes clear that this second derivative is a singular term, okay? So so this will be a boundary value problem, okay, on just the unit integral. We're going to assume that Q is smooth, so we can take as many derivatives as we need for it, okay? And we're going to study first the Q of X is equal to Q constant case. And in that case, we can easily solve for the general solution, which is going to be y of x equals a0 e to the minus x square root of q over epsilon plus b0 e to the x square root of q over epsilon. Okay. Now this is just sums of exponential functions depending on what our boundary conditions would be. You could impose Dirichlet or Neumann or some mixed boundary conditions or something like that. We should be able to specify these coefficients here, okay? Now, about Q, we haven't said specifically anything about the constant Q. It could be negative or positive. So you could either have an exponential function that blows up rapidly or it oscillates rapidly, right? Okay, so if Q is greater than 0, okay, then your solution is going to blow up rapidly, okay? So for instance, e to the square root q x over epsilon, that's going to rapidly climb even before getting to the right boundary there, okay? If q is less than 0, the solution is going to oscillate rapidly, okay? So if, for instance, I look at the real part of e to the square root of q x over epsilon, then I'm going to have something that rapidly oscillates, okay, in between 0 and 1 here, okay? So we can exploit this, right, just as we did when we were thinking about asymptotic approximations of integrals, okay? If something blows up rapidly, okay, then that means that there's some portion of it that's going to matter most. So probably the right side of this function is going to be the part that dominates. Okay. Also, if this oscillates rapidly, okay, maybe we can exploit that somehow in order to approximate the solution. Okay. In general, okay, the WKB hypothesis is that the exponential solution that we're getting here can be generalized, okay, to approximate solutions when q of x is a function, right? So it's a naive assumption, but it ends up working, okay? Now, that's the thing about an ansatz is you can always try it and see if you get something sensible and see if it approximates things well. It turns out in this case, the idea that this function here, okay, is going to translate into having some function, okay, up here that is either rapidly modulating or rapidly causing this exponential to increase, okay, turns out to be a good approximation in a lot of different cases of this particular formula. And not only that, related problems to this differential equation. Okay, so the idea then is that for in general, okay, for our differential equation, we're going to try y is asymptotically approximated by e to the theta of x over epsilon to the alpha to allow us a little bit more flexibility in that solution, multiplied by y0 of x plus epsilon to the alpha y1 of x, and so on and so on, okay, as epsilon gets small, okay, and alpha is greater than 0, okay. So if we do this, then y prime is going to be approximated by epsilon to the minus alpha. It's going to come down from applying the chain rule to the exponential, theta sub x y0 plus y0 prime plus theta sub x y1, and so on up, times e to the theta over epsilon alpha to the alpha. And our second derivative then is now going to have this epsilon to the minus 2 alpha term, theta x squared y0 plus epsilon to the minus alpha theta xx y0 plus 2 theta sub x y0 prime plus theta sub x squared y1, and so on, all of this times e to the theta over epsilon to the alpha, okay. Now we could have taken some expansion here that involved a different scaling of epsilon, a regular scaling, but it turns out this is all the flexibility you typically need in order to tune epsilon to the alpha to the particular potential function that you have out in front of your 0th order term there, okay. So as you can see here, right, once we make this assumption, right, we can go ahead and take our derivatives, and then as you would imagine for your particular function q of x, you're going to select alpha so that it appropriately matches up terms in your asymptotic expansion so that your zeroth order equation has as many leading order terms as possible, okay. Now this is a linear equation, okay, so there's not too much work involved, but you just have this sort of long result from applying the product and chain rules there. So if we sub this into star here and carry out cancellations due to linearity, what we have is we have this epsilon squared term out front, and then we have our y prime prime term. Remember that was this, okay. So I'm just going to write in all of our y prime prime terms here, okay. So I have theta x squared y0 over epsilon to the 2 alpha plus 1 over epsilon to the alpha theta xx y0 plus 2 theta x y0 prime plus theta x squared y1, so on. So that's our y prime prime term, and then here's our y0 plus epsilon to the alpha, y1 plus so on and so on. This all equals 0, okay? And note, we dropped the exponential term because that occurs in all of your terms, right? Because of the linearity, okay? So we're just left with the sort of coefficient functions that precede that exponential, and then also these derivatives of theta, okay? So this is unknown, right? We still haven't tuned what alpha should be, but in order to balance, okay, we can take what? Well, notice that I have an epsilon squared here, and I have an epsilon to the 2 alpha here, okay? This is going to be the, the lowest order term here. And so in order to match it up here with an order 1 term, we need to take what? What should we take alpha to be?
One.
Yeah. All right, let's take alpha equals 1, right? Because this epsilon to the 2 alpha, if we cancel that with an epsilon squared, then we'll get just an order 1 term here, okay? So at order 1, then, we're going to have this special equation, which is going to be theta x squared times y0, okay, minus q of x times y0, okay? Let me just do this in pieces, equals 0, right? But let's assume that y0 is not equivalently 0, okay? Otherwise, to leading order, we have a trivial solution, okay? So if we don't, if we assume that y0 is not equivalently 0, then we have that theta sub x squared is equal to q of x, okay? And this has a special name. It's called the Iconal Equation, and it relates your potential function to the exponential, the function that appears in your exponential function there, okay? So we can solve this, right, for theta. We know q of x, so theta is just going to be some integral involving q. And in fact, we have that theta of x is going to equal plus or minus the integral from 0 to x times the square root of q of s ds plus theta of 0, okay? And note that, funny things are going to happen if q of s changes sign. And that's where we come into what's called turning points, which we'll address in a later section of this part, okay? But all you need to know for now is that, yeah, we can solve for theta just by integrating this equation, okay? So that's our Iconal equation. This is going to give us basically the exponential part of our solution. And now we have to figure out what this leading function is that's going to scale that exponential function, okay? So at order epsilon, okay, what do we get? If I look up here, remember alpha is 1, so this is going to arise in that part as well as this part here, okay? So when I write everything out, I end up with theta sub xx y0 plus 2 theta sub x y0 prime plus theta x squared y1 is equal to q of x y1, okay? So what do I know already in this equation? The only thing I know is theta x, so I could plug that in, but there's an issue here, right? I don't know y0 and I don't know y1, okay? But fortuitously, this part here, right, as long as, well, no matter what, this part here is going to cancel out, okay? Because of the Iconal equation up here, okay? because as long as theta x squared is equal to q of x, these terms cancel out here. Okay, so y1 terms are going to cancel because theta sub x squared is equal to q of x. Okay, so at the end of the day, I can cancel this out, and I just have an equation now for y0. Okay, it's going to be a linear equation with some functional coefficients, right? Some x-dependent coefficients. Okay, so theta sub x y0 plus 2 theta sub x y0 prime is equal to 0. Okay, and so I can do some kind of separation of variables approach here. Let's write this as y0 prime over y0 is equal to minus theta xx over 2 theta x with just some rearranging here. This implies that the log of y0 is equal to minus a half log of theta x plus some constant c. Okay, and this implies that log of y0 is equal to minus log square root of the absolute value of theta sub x plus c. Okay, and when I exponentiate, I end up with y0 of x is equal to c over square root of theta sub x, which if I plug in what theta is, right, from the Iconal equation up here, I get c q of x minus 1/4. Okay, so great. So now I have y0, I have theta. Okay, I have a leading order WKB approximation to my the solution of my problem. Okay, so let me go ahead and write that out now. Okay, let me remind myself. So therefore, y is approximated by what? Well, remember that we said it was e to the theta of x over epsilon to the alpha, y0 of x plus epsilon to the alpha, y1 of x, so on and so on. Okay, so y is approximated by q of x to the minus 1/4, okay, multiplied by a0, the exponential now of minus 1 over epsilon integral from 0 to x square root of q of s ds plus b0 exponential 1 over epsilon integral from 0 to x square root of q of s ds. Close all the parentheses up. Okay, and these a0, b0 constants, okay, they may be complex. And notice what I said before, right? This is valid if q of x is not equal to 0 on x is goes from 0 to 1, okay? Because once q starts switching sign, okay, then I'm going to need to break up this integral, and I'm going to have exponentials that represent different things, okay? Rapidly climbing or decreasing functions, or rapidly oscillating functions, okay? But if it's all the same sign, right, then this never blows up here, okay? And I have exponentials that have the same sort of character of function throughout, okay? So this is our leading order WKB approximation to our sort of basic function there, our basic problem there. Okay. All right. Any questions so far?
Um, so at first I kind of thought that our ansatz kind of looked like something we might get out of doing method of multiple scales. Does this allow us to, like, would this give us different results than if we were to try method of multiple scales on it?
Yeah, because method of multiple scales um, wouldn't specifically prescribe this as a solution, right? Method of multiple scales is not telling you that your solution has the form of a product of an exponential of some function, right? And and a regular perturbation expansion, right? So this is a much more restrictive approach than method of multiple scales. Also, because we're not dealing in um, really two time scale or two scales here, two spatial scales, right? I haven't slipped an epsilon in front of an x anywhere here. So so this is a very specific assumption for a very, kind of specific set of problems that arises very commonly in, certain areas of physics and biology. Yeah. And yeah, I think you probably will get slightly different approximations if you carry out method of multiple scales versus WKB on problems. That's a good question. Okay, so let me say briefly that x values where q of x would be equal to 0 are what are called turning turning points, and we'll address them later. All right. Let's take a specific q and see what happens. Okay, so let's take, for instance, q is equal to minus e to the 2x. Then in that case, y is asymptotically approximated by e to the minus x over 2 times a0 e to the it's minus I e to the x over epsilon plus b0 e to the I e to the x over epsilon. Okay. And we can write this a little bit differently, e to the minus x over 2 alpha of 0 cosine of lambda e to the x plus beta 0 sine lambda e to the x, okay, if lambda is equal to 1 over epsilon, okay. So in particular, in this case, we see that we're going to have oscillatory functions, okay, and their frequency is going to be quite large, right? So the lambda here sort of represents your frequency, but then you have this additional argument. It's not just an x as an argument; it's an exponential as an argument. So we have these sort of modulated oscillating functions, okay, where the argument itself starts to increase more and more rapidly over time. Okay, so commonly in these WKB problems, you have really, really large eigenvalues for some particular representation of the problem. In this case, this isn't really exactly an eigenvalue of a problem, but it sort of serves as a frequency of this of these oscillatory functions that appear in your solution. Okay. Now, if we apply some boundary conditions to this problem, okay. So let's assume some boundary conditions. Let's take y of 0 is equal to a and y of 1 is equal to b. Then we have y is to leading order e to the minus x over 2, b square root of e sine of lambda e to the x minus 1 minus a sine of lambda e to the x minus e divided by sine of lambda e minus 1. Okay. And if we change variables to x tilde is equal to e to the x over epsilon equals lambda e to the x, this implies that x is equal to log of epsilon plus log of x tilde. So dx over d x tilde is equal to 1 over x tilde. This implies that y of x tilde is equal to y of x dy dx tilde is equal to dy over dx over dx tilde is equal to y prime over x tilde. Okay. And d2y over dx tilde squared is equal to minus y prime over x tilde squared plus y prime prime over x tilde squared is equal to minus 1 over x tilde d big Y dx tilde plus y prime prime over x tilde squared. Okay. So the fact that we have solutions like this, okay, implies that this change of variables may tell us something about the original solution. Okay. We're applying that change of variables, and then we're inspecting what we get for the original problem. And in this case, for the original problem, we have x tilde squared d2 y dx tilde squared plus x tilde dy dx tilde plus x tilde squared y is equal to 0. And in fact, this is what's called the zeroth order Bessel's differential equation. Okay. And in general, we can solve this using a change of variables. Okay, like this, and a particular ansatz. Okay. So to get higher order solutions to this problem, okay, you can make this change of variables and use an ansatz in order to get our Bessel functions in this case. Okay. So so for this particular problem here, okay, this is no longer a perturbed problem. in the changed variables, right? The perturbed problem would be in the original variables up here, okay? But this Bessel's sort of problem we can solve using power series in this case, okay? So so let me do that, and then we're going to look at sort of how to approximate the errors of the solution that you'll get to leading order in this case. Okay, so to study this problem, okay, we're going to try solving it with an ansatz where we take y, big Y, is equal to 1 plus the sum from n equals 1 up to infinity an x tilde to the n, okay? Now you can always try power series as the solution to a differential equation, and it's a way of sort of turning a differential equation into a recursion relation if things work out correctly, okay? So so in this case, to zeroth order, it's not hard to show that the constant term that you need in the power series is 1. So I'm just going ahead and plugging that in. Okay. If we plug it into this equation here, we're going to get some power relations in x tilde that we'll be able to isolate in terms of the hierarchy in order to determine the coefficients. So I get that 0 equals a1 x tilde plus the sum from n equals 2 up to infinity an times n times n minus 1 plus n plus an minus 2 x tilde to the n, okay? And of course, we have the assumption that a0 equals 1, okay? So this means that an is equal to minus an minus 2 over n squared, okay? In order to zero out all of these coefficients, okay? I need this coefficient to be 0, right? And so if I write down this is equal to 0 and I rearrange things a bit, I get this equation here, okay? And we also have that a1 should equal 0, okay? Well, so then according to this, that implies that a3 equals 0, a5 equals 0, a7 equals 0, and so on. So we only need the even coefficients. So then we have that a2 is equal to minus 1 over 2 squared, a4 is equal to plus 1 over 2 squared times 1 over 4 squared. And then in general, we have that a to m is equal to minus 1 to the m divided by 2 to the 2m m factorial squared, okay? So that means that 1 plus the sum from m equals 1 up to infinity minus 1 to the m x tilde to the 2m divided by 2 to the 2m m factorial, which happens to be the zeroth order Bessel function of the first kind, or one way to express it, okay, is a solution, right? But remember, this is a second order equation, so we should expect to have two linear independent solutions, okay? So using a similar approach, this sort of power series approach, we also have that, and now this is where my notation is a little bit overloaded, but I'll say y0 here, x tilde equals 2 over pi log x tilde over 2 plus gamma j0 x tilde plus, I'll write it down here, plus the sum from n equals 1 up to infinity minus 1 to the n plus 1 h sub n x tilde squared over 4 to the n divided by n factorial squared. Okay, and this is where is the other. Okay, and this gamma here, it's a special coefficient called the Euler-Mascheroni coefficient, and Hn here, these are what are called the nth order harmonic numbers. It's just what you get by adding up 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Okay, so Hn are the harmonic numbers, and gamma is this thing. It's called the Euler-Mascheroni coefficient. Okay. All right. So the point is, we can get a solution, a second solution to this Bessel function equation, or this Bessel's differential equation. Okay. And that was motivated originally by this change of variables that we followed after we got a WKB approximation to the problem. Okay. So J is the 0th order Bessel function of the first kind. Y0 is the 0th order Bessel function of the second kind, right? So y of x tilde is equal to C0 J0 x tilde plus D0 y0 x tilde. Okay. This is equal to C0 J0 lambda e to the x plus D0 y0 lambda e to the x. Okay. And this, to leading order, is our y also. Okay. Looks a lot different than the leading order approximation we had before. It is different. Okay. But we've arrived at a leading order approximation different. So using our boundary conditions, C0 is going to equal 1 over d b y0 lambda minus a y0 lambda e, and d0 is equal to 1 over d a j0 lambda e minus b j0 lambda. Okay, by just doing, plugging in the boundary conditions, working out some of the algebra, and d here is equal to this difference of products of your first and second order Bessel functions. Okay. All right. Now we have the leading order approximation. Okay. To measure our error, we're going to look at order epsilon squared. And in that case, following a similar process to before, we have 2 theta xx y11 plus 2 theta x y1 prime plus theta x prime y2 plus y0 prime prime is equal to q of x. Now we're pulling in y2. Okay. Now, if you notice from before, the y2 terms again are going to vanish because of the Iconal equation. Okay. So two terms vanish due to the Iconal equation. So that means that we can really, follow up this hierarchy. So we have theta xx y1, 2 theta x y1 prime plus y0 prime prime. Okay, so we just have this inhomogeneous equation for y1. Okay, we're going to make an ansatz for y1, that y1 is equal to y0 of x, w of x, where we don't know w of x. So that means that 2 theta x y0 w prime plus y0 prime prime is equal to 0. Okay, and then we can get w just by integrating. Okay, and there's a couple of possibilities, right? And in particular, I think I'm going to run out of time. If q of x is greater than 0, right? Remember what theta sub x is, right? Theta sub x, right, is equal to the square root of q of x, right? Well, this is going to be real if q of x is positive, okay? So in that case, we handle this equation one way, right? 2 theta x y0 w prime equals minus y0 prime prime. This implies that 2c theta x w prime over square root of theta x is equal to minus d2 dx squared c over theta square root of theta x is equal to d dx c theta xx divided by 2 theta x over 3 halves. Okay, just by working this out. W of x then is given by w prime is equal to a fourth d dx theta xx over theta x to the 3 halves, 1 over square root of theta x. This implies that w of x is equal to 1/4 the integral from 0 to x d ds theta ss divided by theta s to the 3 halves, 1 over square root of theta s ds plus w of 0. Okay, so we can plug in what theta is, right, based on the Iconal equation. And in particular, in general, we know that for any kind of arbitrary problem. Okay, this doesn't just apply to the particular example that we're looking at. Okay, and we'll get some general expression for this w of x then. Okay, so this little detour through this problem, right? It allows us to see that when we take, a particular change of variables here, we get a very specific form of our leading order differential equation, okay, that we can solve. And then to next order, okay, we can find the correction based on this process of making an ansatz and some complicated integration that takes a few steps. But the general idea that we have here is that our WKB ansatz is actually going to be extremely accurate, and so typically you only need to take a single first order approximation to this. So I'll wrap this up, this part up next time, but the idea is that we're going to have a very, very accurate first order approximation. So I know it's getting a bit messy, this sort of next part up, but generally you're just going to stick to sort of first order in order to obtain these very accurate approximations. Because the problem with just doing a regular perturbation expansion is that you would not pick up these exponentially large contributions, which are extremely important in order to accurately represent the solution. Okay, any questions about this? Sorry, I ran a bit over.
So that little aside with the Bessel's equation, I thought we put that change of variables into the original differential equation, right? And so this is the exact solution?
Yeah, well, yeah, to the general problem, right? Yeah. This should be, yeah. So for your, yeah, so for this particular problem, right, we have Bessel's equation as our specific case, right? And so then we can get best sum of Bessel functions as our solution, right? When we return to back to the general problem, this is where we're looking at sort of error corrections in this case for sort of arbitrary q of x in this case. So this is beyond this example, right? This is for any particular case of q of x in this case, not just for the one that we took in that example. Yeah. So this is sort of the end of this example part here. Okay. All right. Well, yeah. As I said, yeah, office hours are normal time. Feel free to stop by if you have homework questions. Otherwise, I'll see you on Wednesday.
Thanks, Zach.
Thanks.